Alright, welcome to this explanation of mass boxes for carbon rigids being used in the carbon rigid body macro. So as you probably all know, in carbon we split the traditional rigid body into rigid shape and body, and you can find explanation about this in our user guide in our documentation. In this section I want to talk about mass boxes, meaning inertia. So let's take a link. We got it nicely here on the origin, and it's a clean geometry. And let's create a rigid body from it. So we go to our macros and automatically creates a setup here. What we got our rigid, our shape, and our body. And it automatically takes the position and the rotation and the extent from using the transform of this mesh and the mesh, obviously. Alright, so that's clean, that was easy. Now let's have a look at two other examples. So let's look at this one first. What I've done here is I simply translated it, meaning I set it translate on the transform of the shape, and I rotated it. You get this. So if I create a rigid body from this, again we get basically the same tight snug fit as we have down here, and it's perfectly aligned. And this is because when you create a rigid body, or specifically here when you create a rigid, we take the transform value. So we take the rotation and the translate of the transform into account and apply it to the rigid, so that we get a nice fitting rigid body, as you can see. Now the problem is, often when you get geometry for modeling, you might get it like this, and maybe best if I hide this one. There we go, and you can see that all of the rotation and the translation is actually baked into the point position of this geometry. So you can see the gizmo on the origin, which indicates that the transform here link 3, the transform has a 0 translate, and it also has a 0 rotate. So really all of the transform, the rotating and the translating is baked into this geometry. And this is kind of the worst case scenario what you can have. So the first thing we need to do when we get geometry like this is we need to center and bake the pivot, because the rigid body will spawn around the pivot point of it, the carbon rigid body. So we select this, we go to modify, center pivot, and you can already see it. Jump here and then bake pivot, and you can see on the translate now this offset that was baked into the points is now moved into the translate here. So as I said, there is the one requirement is to have it here, so we can nicely center our mass box around this geometry. But the other reason for having this word offset not baked into the points but actually have it on the translate is that it increases precision of the internal solver. You could imagine this not only be the case for rigids, but also, for example, for cloths and colliders. So now imagine you have two cloths, and one cloth is spawned at world coordinate 1 trillion, and the other one is also spawned world coordinate 1 trillion and 1. So now they're basically two cloths next to each other, and what happens is when you have the offset is 1 trillion and 1 trillion and 1, if you have it baked into the point position, is you're going to lose your numerical precision, because obviously the way these positions are stored in your computer is limited, so you don't have infinite precision, which means that when now these two cloths collide, almost all of the local positions are kind of almost wiped out by this big offset. So if your cloth is size 1, then obviously all the difference between points 1, 2, 3, 4, 5 of your cloth are going to be super small compared to this 1 trillion offset in the world, and then your cloth collision precision is down very low. So long story short, please try to make sure that your pivot is somewhere in the center or around the center of your geometry. For rigid bodies, you really want it generally up in the center, and you really have this world offset onto your transform. So now that we have this, let's move forward and create a rigid body from it. And you can immediately see the difference now in terms of our mass box. And again, our mass box, our inertia, is on our rigid. The rigid controls this. So this does not affect, as our body is drawn in blue, it will always fit your mesh perfectly, but the rigid is the difference. So here we can see the rotation is 0 of our rigid mass box. And this is again because the transform head rotation is 0. So the transform values are going to be brought in here. The position you can see was the position we had on the link transform. So if I go back to link transform, you see these values, they're taken into account 1 to 1. Now for this link, it might not make a big difference that our mass box is not snug like it is in here, but there are other examples where having a mass box that is not tight fitting as a result of not having your rotation onto the link but backed in. So some scenarios you can get some real issues, and let's look at one of those scenarios. So I just have a scene prepared for you. All right, I already have a collider, and that's kind of just like a thing of a table or floor, and I got two stick or rebar geometries. These two boxes. Let me show you the gizmo for the transform. So the cube one, as you can already guess or see, it has its pivot backed in, and it has the sorry, not backed in, on the transform, and it has the rotation on the transform. So this is actually like if you go back to 0, see it's on 0. Let me show the grid. It's perfectly on the 0. All right. Do. So everything we want is what we can see here. We really have our rotation and our translation on the transform. So all the points are in like on 0 space basically. Now let's look at this one. I wasn't so smart on this one. What happened? I moved in the right direction, but then I didn't rotate on the transform. I actually rotated the points, which means the rotation of this is baked into the geometry. And here we have a big issue because it's rotated 45 degrees. And let's look at the rigid bodies. There we go. Look at this. So this one that had our rotation onto the transform and not back into the points is a very tight fitting, nice, beautiful mass box as you would really want it. Now this one had a rotation 45 degrees baked into the points. And you can see the issue because basically perfectly on the diagonal of the standard layout, we get a mass box that's actually a square. Now, this can cause a big issue. Let's simulate a few frames. And just to remind you, both of these have exactly the same parameters. The only difference is the mass box on the rigid. All right, so they're just gonna fall. They're just gonna kind of hit the table edge and basically start spinning from here. And we're already gonna see much of a difference. So this one that had the rotation set on the transform and henceforth has a very tight fitting and beautiful mass box as we would expect, starts falling off the table and really spins and rolls off. What a beautiful behavior. Now the other one here that had the rotation baked in and resulting in this squarish mass box behaved very sluggishly. As you can see, it just barely slowly rolls off and behaves just completely different to our other rigid body. Now, what's the explanation for this? Easiest is if you think of a figure skater. If you've ever watched figure skating, you're going to notice when they're doing pirouettes, when they're spinning very fast on the spot, they tuck in their arms in front of their chest to really gain speed. So this is this guy here. This one is our figure skater trying to turn as fast as possible, tugging in his arm really tight on the chest. And he gets a nice fast movement. While we have our figure skater here, and what this guy does, he's trying to slow down. He extends his arm left and right as far as he can, and slows down its like the rotational speed by changing the inertia. So it really prevents any small momentum from being created here. It's just a totally different behavior. So yeah, obviously some people might specifically create a mass box like this to create a slow behavior and really get a sluggish effect. You can use it for a lot of interesting behaviors, like our example with our rolling barrel, where you can simulate a basically half full barrel by changing the center of gravity or changing the mass box. There's lots of neat tricks you can do with this, but per default, you would expect this behavior. So I really urge you to make sure to always put your rotational and your translational changes onto the transform. Do not bake it into the geometry, and that can save you a lot of hassle in the long run and make what is very clean geometry. Just to be clear, what you can do is now on this rigid button, the first one, you can still get similar behavior to the second one. You can simply just increase the mass box. Look at this. I can grab my mass box here. So which means I changed the extent here, I scaled it. Let's reset the simulation and go down. So you can still achieve the same behavior. Obviously I didn't have exactly the same parameters, but you can see generally have a very similar behavior, but doing it the right way. We really don't want this. We want our mass box to be tight fitting per default. Alright, I hope this made sense, and let me know if you have any questions.